Sorry, I know it's been a very long setup for this, but so how do we solve Maclaurin series? That's the next thing. And basically, so this idea was first discovered, as far as we know, by a man named James Gregory in the, I think it was the early 1600s. Now, he didn't actually publish his findings because he thought he was just rediscovering Sir Isaac Newton's. Newton did a lot of math regarded to planetary motion, and he thought he just rediscovered Newton's method of doing things. And actually, Newton knew about power series to some degree, but basically, they never really formalized that. They never published math. They never published these ideas. So the first person to actually publish these ideas was named Brooke Taylor in the early 1700s, and that's why we call them Taylor series. But he was the first person to publish these things and really prove. He actually did a lot of hardcore math regarded with infinite series, as we've been studying, kind of to the next level, in order to really prove the convergence that these functions work, even though people had known about them for a little while. And then a little later, another mathematician named Maclaurin did a ton of math specifically with Taylor series centered at zero. A lot of what we're going to do in our class is figuring out using Maclaurin series, and you'll see why Maclaurin series are more useful than Taylor series as we do it. But essentially, the only difference is Taylor series are centered at anything. And so just to do a quick recap, remember, a power series is centered at zero if it's just x to the n, if there is no minus a. But if it's centered at another value, say x is centered at 5, it's just basically the only difference between them. They're basically the same thing. So Matt, what I'll do in class sometimes I'll call them Taylor series, or I might call them Maclaurin series. In my brain, they're the same thing. Maclaurin series is just a specific case to a Taylor series. And yeah, so if they're centered at zero, they're actually a lot more useful. And all of my visualizations are for Maclaurin series. And again, we'll talk about why that is. But the question is, so how did Taylor do this? How did Taylor figure out a formula? And basically, if you look up these things on the internet, you'll find these formulas: Taylor series formula, Maclaurin series formula. What I wanted to show you guys is why. How did they figure these things out? So basically, he started with a very simple assumption. He said, well, let's assume that the Taylor series exists for a function. And so what that means is, if we have a mathematical function, it means it can be represented using an infinite series. Like, for example, e to the x is 1 plus x squared over 2 plus x cubed over 6, and so forth. But the question is, how do we know what that actual infinite series is? How do we solve it? And in general, you can do that. That's what Taylor did. But if we're starting with that original assumption, well, if you remember, a generic power series will look like this. It will have a series of coefficients multiplied by x minus a to the consecutive power. So let me just go ahead and write that again on the notes. So if the function can, now this is a big assumption, and another thing that we're gonna talk about a little bit on Wednesday is, technically this does not always work. Not all functions have Taylor series representations. Only some do. But again, when they do, it's very useful, and when they don't, well, it just doesn't quite work for everything. But basically, what we're going to assume is that f of x, let's say f of x is e to the x, or sine of x. F of x is just any function, and our goal is to figure out what is the Maclaurin series representation of this generic function. Well, basically, if we're assuming it has a power series representation, then it must look like this. In general, it will have to have some series of coefficients multiplied by x minus a to the n power. That's just what a power series is. And if we think about the expansion, that means our function f of x will be represented as c0. And remember, the first term of a power series, or the 0th term, as we say, would be x minus a to the 0 power. That would just be 1. So basically, it'll just be a constant term. C0 is just going to be a numerical value. And then, so the first term would be c1 x minus a to the first power, then c2 x minus a squared, and so on. But basically, I'm actually going to write out 5 or so terms, because we're gonna need these terms as we look at the derivation of a Taylor series. And for now, if you're wondering why are we doing this, but basically, if a function can be represented as a power series, well, this is what a power series is. It will just look something like that, where C0, C1, C2 are just numbers, and A is a number, and we don't necessarily know what those things are. So what's the point? Well, what actually mathematicians noticed, including so James Gregory was the first person whose math we can find who actually did this. But again, Brooke Taylor did formalize and another rule of thumb with math: if you're discovering new math, you need to publish your results. If you don't publish it, the history will not recognize or remember you. Well, in this case, James Gregory is still remembered as being a well-renowned mathematician, and he did other stuff as well. But obviously, we don't call it a Gregory series. We call it a Taylor series, even though it wasn't necessarily his idea. Anyways, so if you think about taking the derivative, that's one thing that's useful. But actually, if you think about plugging in the central value of the polynomial. So one thing about this is, well, we have some C0 plus C1 x minus a. If you consider what if x is equal to a, and this is one thing that is necessary for the proof. Well, this is a general thing with polynomials, right? If you think about a polynomial like x squared plus 4x plus 5, so let me just write what I'm thinking, because I'm trying to help you see this idea. If you plug in particular values, like for example, say I plug in 0 into f of x. And so generally we'd say the center is at a or 0 for something. What would happen is I'd have obviously 0 plus 5. But what happens is if you plug in 0 or the central value of a polynomial into it, all of the terms will be 0 except for the constant term. And that's exactly the idea that we can use for the proof, right? Because let's say I plug an a into the function. Well, again, if f of x has a power series representation, I can plug whatever I want into it, assuming it converges at a. And if I plug in a, well, notice what I would get is, well, C0, that's just a constant that's not affected by a. And I would have C1 times a minus a plus C2 times a minus a squared. But basically, I'm plugging in a value for x into an infinite series. But what you'll notice, why is plugging in a cool or useful? Well, if I plug in a into x minus a, it will be 0. And I will get C0 plus C1 times 0 plus C2 times 0. Basically, this will go to 0, this will go to 0, 0, 0, 0, and all of this will be 0. So essentially what I'm saying here is that if you plug in the center into a power series, all the terms will be 0 except for the leading coefficient. And again, so why do we care about that, or why is that useful? Well, what this is implying is that if a function has a power series representation, then the first term, the constant term, must be equal to the a value of the function. And actually, that kind of makes sense based on the visualization we were just looking at, right? Because notice that actually where these two graphs intersected was at the value of 1. And if you look at the value of f of x, 1 over 1 minus x, if you plug in 0, you get 1. And the first term of that expansion was also 1. Because as we look at the expansion, it's sort of like we're trying to weave around that function, and it has to start at the intercept. And that's exactly what this is saying. And if x is a, basically, for a power series centered at a, the center is just the point where you're starting your wrapping the function around. I kind of imagine as you're wrapping the function up to try to create a polynomial that fits that function. And you need to start at a. But this is showing us why, if we start at a, the first term of the coefficient must be equal to a if this thing works. So, but where do we go from here? So also, if you're wondering, okay, what is the goal? What are we trying to figure out right now? The goal is to figure out if we can figure out the series of coefficients. That's the only unknown, right? Because if it's a power series, it will always be x minus a to the consecutive power. The only things that we don't know are what are the coefficients? What is C0? What is C1? What is C2? And so on. And basically, there is a pattern. There's a cool pattern that emerges, and that's why we know certain functions have Taylor and Maclaurin series representations. But so where do we go from here? How do we now we know that C0 is equal to the y-intercept of the polynomial. So, but what about C1? What about C2? But basically, let's say we were considering the derivative of f, and that's exactly where the proof comes next. And again, this is what James Gregory and possibly even Newton had found previously, as the inventor of calculus, one of the inventors of calculus. He did a lot of awesome math. But anyways, well, if you think about this, basically C0 is just a constant term, right? This is just a number, whatever number is 1, 2, 1/2, it's something. But if we take the derivative with respect to x, that will be 0. So for right now, if we're taking our power series representation, I'm asking you to consider what happens as I take the derivative of f and solve f prime. But basically, the first term, the derivative of C0, a constant, will be 0. Now, looking at the next term of the power series representation, the derivative of this with respect to x, well, I have a coefficient which will not be affected by the derivative, and then I would need to take the derivative of x minus a. So the derivative of x is 1, and the derivative of a is 0. So what I would get is C1 times 1 as I take the derivative of the next term. And since it's a power series, right, I can solve the derivative term by term. These are all polynomials, right? Polynomials are very easy to differentiate. That's, again, another reason why power series representations of functions are cool and useful. But now moving on to the next term of the expansion, here, if we solve the derivative of this one, well, again, C2 is a coefficient, will not be affected by the derivative. I can pass that through. And if I take d dx of this, I'd have x minus a squared. Well, if I use the extended power rule, right, I could drop the 2, which would give me the derivative of this, and subtract 1. So I would have 2c2 x minus a to the first power. And technically, I would need the chain rule because the inside is more than just x, right? Because I'm not just differentiating, I'm differentiating x minus a, but the derivative of the inside, as we've already established, is 1. So I'm going to ignore the chain rule throughout because it's x minus a. Derivative of x minus a is still just 1. But basically, I'm using the power rule, right? The derivative of this, I drop the power and subtract 1. And I'll just go ahead and erase this first power here. And I'll erase this 1 because, just cleaning up my math a little bit. Now, moving on to the next few terms, and that's why we needed more terms in our power series expansion. Well, the derivative of this term of the power series, I need to drop the 3 and subtract 1. So I'd have 3c3 x minus a squared. That parenthesis came out looking a little straight. The next term's derivative, I would drop the 4 and subtract 1. So I'd have 4c4 x minus a cubed. The next term, I would have 5c5 x minus a to the 4th. But basically, and so on, right? If it's an infinite series, I would need to continuously differentiate those terms forever. But basically, there is an underlying pattern behind the infinite differentiation of that infinite power series. And at the end of the day, let's also erase this plus 0. But at the end of the day, this is what f prime will have to look like, right? If this is my power series representation for the function, its derivative will have to look at like this. And then the next thing you might notice is, well, what if we look at f prime of a, right? Because up here, we notice that f of a is the 0th coefficient of the power series. If I plug in a into the derivative, well, notice that, C1 is a constant. This term will not disappear, but the remaining terms, right, they've all lost 1 power as what happens when we differentiate a polynomial. But all the remaining terms will still head to 0, right? Because this will be a minus a squared. This will be 0 plus 0 plus 0 plus 0 plus 0. And so what I'm going to be left with is f prime of a is equal to C1. And what this is saying is that the next coefficient on our power series must be equal to the first derivative of that function evaluated at a. And actually, if you look at this, the graph of this is kind of very helpful. But if you look at the graph of 1 plus x that we looked at a minute ago, notice that the slope of that was equal to 1. Not coincidentally, if that matches the slope of the function at the intercept. Very interesting, right? And that was the second term of the expansion. And it turns out that if you continuously differentiate, the second order derivative gives you the next term. The third order derivative gives you the next term and so on. But it's sort of like taking higher and higher order derivatives, taking the concavity, taking the jerk, taking, if you continuously add up those components, it will recreate the original function. Very, very fascinating. But basically, let's finish up the derivation, because basically if we keep differentiating, we can continuously solve more coefficients. And what I want to ask you guys in just a minute here is, do you see the pattern? Like basically the final pattern that exists in a Taylor series. But basically, let's look at f double prime, and then what we'll do is we'll plug in a. Then we'll look at f triple prime, and then we'll plug in a, and so on. But basically, there is a pattern that emerges. And remember, with higher order derivatives, we represent, the prime notation means first derivatives, 2 primes means 3, and so on. Eventually, we use just the notation f4x, which means the fourth order derivative, and so on. So basically, what we're going to do is we're just going to keep solving the derivatives until we can figure out the pattern. And at each case, what I'll do is I'll highlight. Let me use a bigger highlighter. I'll highlight kind of the final conclusion from each order of the derivatives. So if we go to f double prime, well, the second order derivative is just if we take the derivative of the derivative, right? Because this is our first derivative, I'd need to differentiate again to find f double prime. But notice that in the second order derivative, the derivative of c1 will go to 0. The derivative of this, x minus a, will go to 1. So this would just leave me with 2c2. The derivative of this term, I'll drop the 2. So it would leave me with 3 times 2, which is 6, c3, and then times x minus a, because I'm going to drop the power and subtract 1. Here, I'm going to drop the power and subtract 1. So its derivative would give me 12c4, x minus a squared. And then moving into this term here, I drop the 4. 4 times 5 is 20. X minus a cubed. And actually, let's use one more term just in case we need it. But the term that I did not write here was c6 x minus a to the 6. Its first derivative would have been 6c6 x minus a to the 5th, right? Because I would drop the power and subtract 1. So the next term would be 6 times 5. We probably don't, we may not need this term, but we'll just go ahead and write them all out just in case. But basically, so this would be the second order derivative of the power series. And sorry, I wrote the C2, that should be C2, not C squared. I put the 2 in the wrong place on accident. But basically, our second order derivative of the power series representation will look like this. Again, if we plug in 0, or if we plug in a into this will be 0, 0, 0, 0 forever. So again, this will continue, as I should write this out using the ellipsis. But basically, if I plug in a into the second order derivative, I'll just be left with 2c2. And we need to do a few more derivatives to really finish making sense of this. So let's just keep going. The third derivative, well, again, the derivative of a constant will be 0. The derivative of this term will just be 6c3. The derivative of the next term, I'll drop the 2, and I would have 24 c4 times x minus a. Then 3 times 2, 3 times 20 will be 60. But it turns out that the coefficients, they get kind of crazy, kind of gross. But there is a pattern, and that's what we can make use of. And then in this one, I would drop the 4. 4 times 30 is 120. And then if I plug in a into all of this, again, all of these terms will go to 0, and I'm going to be left with just 6c3. Because it's always just a constant term that is left when we plug in, the 0 value of the polynomial, or the center of the polynomial. So the fourth derivative, and again, getting a little tedious, but I think, we're almost there. We're almost done. So from the third order derivative, I take the derivative of this. This will go to 0. The derivative of this will be 24c4. Again, x minus a derivative will be 1. This derivative, I'll drop the 2. It will be 120c. Whoops, sorry, that was a c5. I just noticed I did not write c5 here. And this should have been a c5. So sorry, I'm messing up. Hard to talk and write all of this apparently. But yeah, derivative of this term will be 24c4. Drop the 2, I'll have 120c5. X minus a will go to the first power. I'll drop the 3 here. I'll have 360 c6 x minus a squared, and so on. And the fourth derivative evaluated at a will just be 24c4. And that's the important thing to figure out. And going one more just for the heck of it. But obviously, you can continue doing this forever, right? It's an infinite series. Technically, it's an infinite number of terms. This derivative is also an infinite series, but there's a pattern behind the derivative of an infinite series. That's the essence of a Taylor series. And so the derivative of this will be 0. Derivative of this will be 120c5. And then derivative of this will be 720c6 x minus a, and again, so on. It will keep going. And the fifth derivative's term evaluated at a will be 120c5. And there we have it. So basically, let me return back to the original problem. So in order to figure out a Taylor series, we're going to assume that a function has a power series representation for it. And as I was saying before, really the only thing that we don't know about it is the series of coefficients. Because in general, a power series always is an infinite sum. It always has x minus a to the end, right? That those components are the same throughout. The only thing that we don't know in that is what is Cn. And the point is, if we elaborate and we continuously take the derivative, we can figure out that the coefficients have a particular pattern. Now, if we were to take each one of those and solve for the coefficient, well, this, for example, in this one, what this would do is it would say that C2, if we divide both sides by 2, we would have C2, it must be equal to the second order derivative at A divided by 2. The third coefficient is f triple prime of a divided by 6, and so on. But essentially, there is a pattern, and the pattern is the series of coefficients that we have on those. And essentially, there is a pattern behind the sequence of numbers. And if you notice, there's a sequence of numbers here, which is 1, 1, 2, 6, 24, 120. And so here's my question for you guys: Does anyone recognize what this pattern is, what this mathematical function is? The series of numbers 2, then 6, then 24 as a mathematical function representation. Sorry, I know I haven't paused to ask you guys questions because I've been talking so much. But so maybe let me give you a little hint. If let's say we look like we backtrack across these numbers and kind of where they came from. So if we try to keep track of these numbers, right? 120c5, it came from this term in the expansion. So let me highlight it all the way back to where we started. And if you look at it, right, this was from the fifth order derivative of the function. It started with the, technically the sixth term of that power series function. It started as just c5x minus a to the fifth. As we took the derivative, we dropped the 5, then we dropped the 4, right, and that made 20. Then we dropped the 3, then we dropped the 2. So basically, 120 is comprised of 5 times 4 times 3 times 2 times 1. Similarly, if we keep track of the term right before it, this one, right? Notice that it started with 4, times 3 times 2 times 1. So those sorts of patterns, like 4 times 3 times 2 times 1, 5 times 4 times 3. Does anyone recognize, like, so mathematically, yeah, so okay, Dad just put in chat factorial. That is exactly what it is. So this pattern of the series of coefficients that we get as we repeatedly differentiate is a factorial. And actually, that's the generic, if you take a higher order derivative of a polynomial, say, for example, x to the 4th power, you get 4x cubed. If you do it again, you get 12x squared. If you do it again, you get 24. Basically, the series, because if you start with a power of 4 and you differentiate, you multiply by 4, right? Then you reduce by 1, then you get 3. Then you multiply by 3. Basically, you're taking the power, you're multiplying by the next consecutive power and the next one and the next one. And that is what a mathematical factorial pattern represents. Very, very awesome, very good. And that's exactly what Brooke Taylor and James Gregory discovered, and that's what's so cool about all this. So anyways, so let me try to write this formula in a more concise fashion. If we want to know the general nth derivative of a function evaluated at a, basically right here, what we'd have is the nth derivative evaluated at a must be n factorial cn. And basically this formula that I'm writing right here is the solution. And how we figured that out is because that's a factorial pattern. Once we recognize that the series of coefficients on the higher order derivatives is a factorial, what this leads us to conclude is if we continue this pattern forever, right, the nth derivative of the infinite power series evaluated at a will always just be 5 times 4 times 3 times 2 times the particular Cn. And notice that this formula encompasses all of these, right? If I plug in 2, that matches here, right? Because 2 factorial is equal to 2. If I plug in 3 for n, I would get the third order derivative is 3 factorial C3. The fourth is 4 factorial C4. The fifth is 5 factorial C5. And basically that pattern will continue because that's what the nth derivative of a power function will be in this particular manner. Not easy to figure out, but basically, hopefully that makes some sense to you as to why that pattern happens. Now, also, we can take this and solve for Cn. This is the final solution. If we divide by n factorial from both sides, what we would conclude is that the nth derivative of that each consecutive coefficient, this is the final formula for a Taylor series polynomial, is the nth coefficient is equal to the nth derivative evaluated at a divided by n factorial. And basically, TLDR, summarizing all of this, if you're trying to solve a coefficient of a Taylor series, you just you can plug it into this formula. This formula will give you the proper answer. And so on the next page, basically the summary conclusions are listed there. The Taylor series of a function, and notice it says assuming it converges in its interval of convergence. So again, as I was saying at the beginning of lab, it has to converge to the function, right? If it does, sometimes it may not converge. Well, we'll get into those details soon. But basically, if the Taylor series does work, then it will look like this. The function will be represented in this form. And if you were wondering earlier, so how did we come up with these formulas? Basically, you can figure it out by using the formula. You can always rederive them from scratch, but basically this is a generalized formula for any function as represented by an infinite series. And so also a Maclaurin series, as I mentioned, is a Taylor series centered at 0. Why that's a lot simpler is because as we were doing all this math, right, it was pretty annoying because we had all these x minus a's and so on. But basically, if you just center it at 0, it's much, much simpler. If you do all of this with basically, you'd be, instead of using f of a, you'd be using f of 0. The proof would be exactly the same. Everything would work exactly the same. The math would just be simpler because we're going to have C0, C1. We just have x here, not x minus a, and then x squared, x cubed. It's a more basic power series centered at 0. And if we do it centered at 0 and do all the same things using 0 instead of a, this would be called a Maclaurin series instead. And what we'll be doing is we'll be deriving the Maclaurin series representations for functions and talking about how they convert. So I'm almost done. Sorry, I know this has gone on for a long time. I didn't really know how long this would take, but it's a complicated derivation and I didn't want to rush over any of the ideas. But basically, what we'll do is let's look at e to the x, because our lab for this week, sorry, I know we've been away from what this lab's all about for quite a while, is if we had e to the minus x squared and we can't solve its integral, as I was saying earlier, how do we figure that out? Like, how do we solve this integral? Well, we can use the Maclaurin series representation for e to the x to do that. So what is it? The formula, again, it's in the book, it'll be on the cheat sheet on the test and so forth, but the formula is here. And the first question is, how do we find it? That's what I wanted to do next, is how do we actually find a Maclaurin series representation? But basically, if you look at it, well, what we need to know is the conclusion here is the coefficients of the series are the nth derivative at a divided by n factorial. Or if we're doing so this would be for Taylor. If we want to change this to a Maclaurin series, all you need to do is change it to 0 instead of a. It would be the nth order derivative evaluated at 0 divided by n factorial. And again, that's just easier because instead of plugging a in, we're going to be plugging in 0, which is usually an easier number to evaluate in a generic function at the end of the day. But if we want to find a Taylor Maclaurin series, basically what you need to do is you need to repeatedly differentiate the function. Let me just copy this down. Repeatedly differentiate f. And generally there's a pattern. So basically it's like, can you figure out the pattern? So I'll write pattern ? And then you need to plug in the center. So plug in x is equal to 0 for Maclaurin series, or x is equal to a for a Taylor series. And those are your coefficients. So it's actually, it's sort of simple at the end of the day, but it's a very, why do we do all these things? That was the point in the of this example, is that you can solve the coefficients of the infinite power series and how it must all add up if you look at the consecutive derivatives. So let's look at e to the x. Let's derive e to the x today, and then in class tomorrow we'll keep talking about it, and we'll look at, say, sine and cosine. But essentially, a lot of our elementary mathematical functions, such as trigonometric functions, exponential, logarithms, rational functions, often you can take those functions and represent them as power series or as Taylor Maclaurin series.